Now in the previous lecture we have learned how can we create a binary search tree. Now in this lecture we will talk about how can we insert a node into a binary search tree. Now when we insert a node into a binary search tree, we have two options over here. The first option is a root node is blank, so it means that it's a blank tree, so we don't have any element in this binary search tree over here. And the second case is binary search tree has some nodes. So it's obvious that in the first case, if the binary search tree is blank, inserting a new node is very simple. Here, all we have to do, we are creating a blank node and inserting value to it. Then we are letting root of this binary search tree to point to this node over here. So this is a very simple case. Now in the second case, in which we know that we have some elements in our binary search tree over here. So let's say we want to insert this node in which we have value of 10 to this binary search tree over here. So we have to start from root node and traverse toward left and right children to identify this node over here. Now here you need to keep in mind that whenever we are inserting a new node to the binary search tree, we have to take into account two properties of binary search tree, in which it says that the nodes that are less than and equal to root node are located on the left, and the nodes that are greater than the root node are located on the right. So whenever we are inserting a new node to this binary search tree over here, we have to take into account these rules over here. So this means that when we insert a new node, we will compare the value of new node with the root node. So if it is smaller, we are going to continue to the left part. If it is bigger, we are going to continue to the right part. Now in this case, the value that we want to insert is 10. So in this case, we are going to compare 10 with the root node. So if we compare 10 with the root node, which is 70, we see that 10 is less than 70. So this means that we are going to continue to the left subtree. So we don't need to go to the right subtree in this case, so we are eliminating right subtree from this traversing over here. Now, if we continue to the left subtree, the first child is 50, so one more time we are going to compare if 10 is greater than 50 or less than 50. So if it is greater, we are going to continue to the right child. If it is less, we are going to continue to the left child. So in this case, we see that 10 is less than 50, so this means that we are going to continue to the left child. Now in the left child, we have the value of 30. So here again, we are going to compare. If 10 is greater than 30, we are going to add it to the right child. If 10 is less than 30, we are going to continue to the left child. So it's obvious that 10 is less than 30, so we are going to continue to the left child. So in the left child, we have value of 20. So one more time, we are going to compare whether 10 is greater than 20 or not. So in this case, we see that it is less than 20. So this means that we are going to add this node as a left child of 20 over here, because in this case, the property of binary search tree says that the nodes that are located in the left are less than the root node. So that's why we are going to add it as a left child over here. Now let's look at another example. So in this case, for example, let's say we want to add 95 to this binary search tree over here. Now here again, we are going to compare 95 with the root node. Now in this case, we see that 95 is greater than the root node, which is 70. So this means that we are going to continue to the right child of this binary search tree over here. So when we are continuing to the right child, here in this case, we see that we have 90 over here. So one more time, we are going to compare 90 with 95. So we see that 95 is greater than 90. So this means that we are going to continue to one more time to the right child. Now when we reach the right child, we see that in the right child, we have 100 over here. So this means that we are going to compare 100 with 95. So we see that 100 is greater than 95. We don't have any child for this 100 over here. So this means that this node will be added as a left child to the 100 over here, because in this case 95 is less than 100, so it can be added only as a left child. So with this, all properties of binary search tree are satisfied. Now this is how the logic works in case of binary search tree when we are inserting a node to the binary search tree. Now based on this logic, let's head over to Java and create our insertion method in practice and see what is the time and space complexity for this method over there. Now here, inside this binary search tree class, we are going to implement our insert method. Now before implementing insert method, we are going to implement a helper method which will return the type of binary node. Then we are going to assign this binary node to the root node inside main insert method. So here, our method will be like this: private binary node. So I'm going to make it private because in this case, we are just going to call this method inside this class. So we are not going to call outside of this class, so that's why I'm going to put private. So the return type of this method will be binary node, and the name of this method will be insert. So this method will take two parameters. So the first parameter will be the current node, and the second parameter will be the value that we want to insert into this binary search tree over here. So the first parameter is binary node, current node, and the second parameter will be type of integer with value. Now here, first we are going to check that if the current node is null, in this case we are going to create a new node and assign a value to it, then we are going to return that node. Because inside main insert method, we are going to assign the value that returns from this method to the root node. So that's why in this, we are just going to create a new node and return that node. So here it's going to be like this. If current node is equal to null, in this case, we are going to create a new node, binary node, new node is equal to new binary node. Then we are going to assign the value that we are getting from the here as a parameter to this new node over here. So new node.value is equal to value. Now after doing so, we are going to print out to the console saying that the node is successfully inserted to the binary search tree. So I'm just going to put over here system out print, and inside this print statement we are going to put the value successfully inserted. Now after doing so, we are going to return this new node that we created over here, because as we said, we are going to set this return value to the root node. Now this case over here, this if condition over here, is a base condition for our recursive call that we are going to call. Because as we said before, when we are inserting an element to the binary search tree, if the value is smaller than the root node, in this case we are inserting to the left child. If it is greater than the root node, in this case we are inserting it right child. So this means that we are going to call our method for left child and for right child recursively. So for recursive calls, we need to have a base condition. So this is going to be the base condition for our recursive calls. Then in the else condition, we are going to check that if the value that we want to insert is less or equal to the current node's value, in this case, we are going to insert it in the left subtree. So it's going to be like this. Else if value is less or equal to current node's value, in this case we have to add this one to the left child. So in this case I'm going to put current node that left is equal to, we are going to call this method, insert method recursively for the left child. So in this case it's going to be like current node dot left, and as a value we are going to put value. Now after doing so, we are going to return the current node. So because in this case we are adding it to the current node, so that's why we have to return current node. Now in the else condition, if the value is greater than the current node's value, this means that we are going to insert it to the right child. So I'm just going to copy this part from here and pass it over here, and instead of left I'm going to put right, and here also I'm going to call it for right child. Then at the end we are going to return current node. Now with this we have successfully implemented our insert method over here. Now basically, instead of calling this method every time for root node, so that's why I'm going to create another method over here, which will be the main insert method. So it's going to be like this, insert. So it's going to take as a parameter only value. Then inside this method, we are going to call this method that we created over here. So here we are going to call it for first node will be root node, and the second parameter will be the value. Now with this, we have successfully created our insert method over here. Now let's see how this is working in practice. So inside main class, before we have created our new binary search tree like this, so here based on this new binary search tree, we are going to call insert method over here. Now as you remember, when we are talking about the binary search tree, we had a binary tree like this. So I'm just going to create this binary tree over here. Now here the root node is 70. So I'm just going to call insert method and call for the 70. And I'm going to continue to add all other nodes over here. So the left child is 50, then the right child is 90, and we are adding all other childs over here. Now if I run our code, you'll see that all nodes are successfully inserted to this binary tree over here. So it's printing out for all the cases that the value successfully inserted. Now with this we have completed our insertion method. Now let's see what's the time and space complexity for the insertion method in case of binary search tree. Now here again, as always, we are going to start from the first line of this method. In the first line, we are checking that if the current node is null or not. So in this case, if it is null, we are continuing to do some operations over here. So this if condition over here will take a one-time complexity. Then inside this if condition, we are creating a new node and assigning a value to it. So these two lines of code will take a one-time complexity because these are just simple assignment statements. Then we are printing out to the console this message saying that the value successfully inserted. So this one also will take a one-time complexity. Then at the end we are returning new node. So this one also will take a one-time complexity. Now in the else if condition, we are checking that if the value is less or equal to current node's value. So we know that if condition like this will take a one-time complexity, then we are calling insertion method recursively only for left child. So this means that in this case, the time complexity for this line of code over here will be O(n) divided by 2 time complexity. Then we are returning current node, so this one also will take a one-time complexity. Then we are continuing to the else condition. Now in the else condition, we are calling this insert method recursively for the right child. So this means that this part of code will take O(n) divided by 2 time complexity, because in this case we are just calling it for the right child. Now then we are returning the current node, so this one also will take O one time complexity. Now if you combine all these complexities over here, we will get all again time complexity. Now you might be interested, how did you find the all again time complexity? So one more time, if you want to get detailed information about for finding time complexity for recursive calls, I advise you to go back to recursion section of this course over here. Now here you just need to take into account that whenever we are inserting a node, we are going to call our method recursively for left subtree or for right subtree, because if the value is less equal to the current node's value, we are going to call it for the left child. If it is greater than the current node's value, in this case we are calling it for the right child. So this is the main reason that the time complexity will be O log n time complexity. Now the space complexity is also O log n, because here again, whenever we are calling a method recursively, in this case we are inserting the nodes to the stack memory to remember for the next case. So one more time, here again, the reason for the O log n space complexity is that we are going to call it either for left subtree or right subtree. In this case, we are not going to call for both of them, so that's why the space complexity is also O log n. Now with this, we have come to the end of this lecture. So in this lecture, we have explained how can we insert a node to the binary search tree, and we have implemented in practice. So hopefully everything is clear about insertion of a node to the binary search tree. So see you in the next lecture.